All right, so sorry about the delay. Please take a seat so we can get this course started. Okay, so welcome to today's class in Mathematics 1. This is the first class of week number 2, so I hope you've all watched the videos for week number 2 by now. Today we'll start our discussion of linear equation systems, and this is a hopefully easy part of this course. I guess most of you have seen linear equation systems in some way or the other. Maybe you're not yet acquainted with the Gaussian elimination method. Maybe you are acquainted with that, all the better. We will use that method mostly as a tool in many, many places in this course, and it will also play an important role in other courses, most notably management science. So even if you know this already, you should pay attention to what we are doing here, because it will be important. All right, before we start, I'd like to take the chance to have a quick look on TweetBack here. I'd like to know whether you already have worked with Gaussian elimination in the way that we are doing it in this course, basically. So just to get a quick feedback from you here, maybe you can open your phones or notebooks, go to this link. This is the feedback link for this week, and answer that question for me. And just as a side note, to keep things a little more organized for me, I'll have a different feedback link for every week. So that is especially important for the chat wall. I'll monitor the chat wall for each week, basically until a little after the end of that week. And after that, I'll switch over to the next one. So please try to not write any questions in the old chat walls anymore. I'll close those at some point. But if you find there's no answer, try asking on the forum or on the up-to-date, on the current chat wall once again. Yes. Yes, sure. Let me see if I can tune that up a little. Yeah, too much. Is that better? Too much? All right. Okay, so let's have a look at the quiz results. I'll give you a couple more seconds. Let's say 10 more seconds before we close that. All right, so let's take a quick look. So here's the result. A little more than half of you have already worked with Gaussian elimination, which also means that less than half of you have not worked with that before. So we are going to practice this quite a bit this week. There's not that many new topics, hopefully, but we'll have some more time for practice this week. Just as a warning, this will change in the coming weeks. There'll be a lot of things you might not have seen. All right. Second quick question before I proceed. I hope you did also have a look at this homework problem here. Simple 2x2 system of linear equations. I'd be interested in the solution that you have found for that before we discuss that in more depth. And I'd also like to know how hard you found that. So again, let me quickly switch to TweetBack. The quizzes are open on TweetBack now. And while you're voting, I can also tell you I'm trying a live stream today, so I'll have another approach at doing a live stream and hopefully also a recording of this course. We'll see how this turns out. Seems to be working at the moment. I hope the network here in the room is going to be stable enough for that. All right, let's take one more minute to collect all the votes. All right. So I can see most of you got the right solution here. X1 is 2, X2 is 3. So that should be the correct solution. In fact, if you haven't gotten that, be sure to check the suggested solutions later on. And as for how hard you found that, most of you are thankfully leaning to the easy side. I'd also say this should have been a rather easy problem. Okay, we'll have a look at some more example problems later on. So let's start quickly going through the notes of this course. So I guess this will be a rather quick walkthrough because there's not that much to talk about, but let's have a quick look at the course notes here. So we started with an application, basically meant to give you a motivation and also an example to help you see that this is something that is really relevant in practical applications. I don't think we need to go over that in more detail. So let's get down to that definition right away. A system of linear equations, that is a system that consists of a certain number of equations, as the name suggests. Usually I'm using the number m for those equations, or I also refer to equations as rows for reasons that will become clear later on. And there's a number of variables. I usually use the number n for variables. And I might also refer to those as columns. And then, of course, you also need a right-hand side. So those two, the numbers, the equations, and the variables, those form the left-hand side of your equations. You also need a right-hand side. So for each of the equations, there's some number, beta I here, on the right-hand side. And then we have coefficients in these equations. So we usually have, right, the equations in the most general form in this way here. So each row forms one equation. Here's the right-hand side. Here's the left-hand side. The variables here are denoted by x1 to xn. And the coefficients, those are constant coefficients that go with these variables. Those are, in this case, denoted by alphas with two indices. The first index is for the row, so the equation number, and the second index is for the column, so the variable. Right, so we here have we have alpha 1, 1, alpha 1, 2, and so on to alpha 1n. Second row, we have alpha 2, 1, alpha 2, 2, and so on, up to, in this case, the mth row with alpha m1. Right, so just a very general form to formalize this. And then we say such a system is feasible if there exist values that I can substitute for the x's in all these equations at the same time. And all these equations are simultaneously true. So they all evaluate to their respective right-hand sides. If something like this exists, the system is called feasible. And each possible setting of the variables that satisfies the equations is called a solution. Should be immediate. A set of all solutions, I will refer to those as the solution space or set, or sometimes as the feasible region or the feasible set. And then one thing that might be new, we distinguish between two kinds of systems with linear equations depending on the right-hand side. If the right-hand side is all zeros, we'll call the system homogeneous. And if it's not, we'll call it inhomogeneous. The reasons for why this distinction is important will become obvious next week when we talk about vector spaces. And a couple of solution methods that you hopefully have already seen. One method that seems popular. All right, so that's something that is easy if you only have two equations. It becomes increasingly harder if the number of equations increases. So for 3, 4, 5, 6 or more equations, this is something where I tend to lose my focus here. So I tend to make a lot of errors trying to do this in larger equation systems. So I recommend, you can do this for small equation systems if you're comfortable with that, but I recommend not doing it for large equation systems. You easily make mistakes this way. Okay, so here's a quick geometrical look at things. And that's also something that you should keep in mind, what the geometry behind these equation systems is. If we have two variables, means the solutions somewhere live in this plane here. Yeah, so we have one axis for the x1 variable, one for the x2 variable. And we can just draw all the feasible sets for one of the equations. Where for this first equation here, all pairs of x1, x2 variables that fulfill this equation lie on a line, and you can easily see this by solving, for example, for x2, right? You just get a linear equation that corresponds to a line in two-dimensional space. Same thing for the other equation here. Just get a different line. And then, of course, the set of solutions for the whole system, that just is all the points that lie on all of the lines. In this case, we have two lines, and those intersect in exactly one point. So there is your solution. It's always helpful to have this geometric intuition in mind. However, for solving these problems, you should usually resort to numeric methods. Right? Geometry might not be that exact. And also, we usually won't bother too much about two-dimensional systems. Those are boring. And drawing these things in higher dimensions becomes tedious quickly. All right, different solution approach. You can look at this system here. One approach that you should also know from school probably is subtracting one equation from the other to get a new set of equations, and hopefully one that is easier to solve. And you cannot just subtract equations from one another, you can also multiply them by any constant number other than 0, of course. Yeah, using 0 would mean you basically nullify the equation, so you lose information. You don't want to do that. But for example, I could multiply this first equation here by 2. So this is the first equation in the original form. I multiply that by 2, and I get the exact same, left-hand side here as for the second equation. And that means if I subtract this first equation from the second, right, what I get is just a bunch of zeros on the left and also on the right-hand side. Same thing on the right-hand side as well. So an equation like this here, 0 is 0, well, that is obviously always true. So we don't have to bother with that. So basically the set of feasible solutions is determined only by this first equation here. And in this case, that means we can solve this for one variable. I opted for x1, you could also do x2. And that means for each value of x2 that we choose, we can compute the corresponding value of x1 such that that pair is a feasible solution. So there is an infinite number of possible solutions. Each value of x2 gives us a corresponding x1 value, and we get an infinite number of feasible pairs here. And usually express this in a way like this. Right? So you write the x1 value, the x1 value here on the first row, the x2 value on the second, and the x2 value is just anything you like, arbitrary, just x2. And say, well, I can do this for all possible x2s, and usually the ground set here is the real numbers. So that is the set of feasible solutions. And to get a clearer idea of how that looks like geometrically, you often rewrite it in that way by splitting off all the constants, so everything that is not associated to x2, and all the coefficients that are associated to x2 to do different vectors, right? So this is the constant part, and this here varies. And well, geometrically, what you have here is you have this point 40, that is this point here. And then there's this -2,1 that's added at this point. So if you go here, if you add -2,1, that means we're moving 2 in this direction, 1 in this direction, so we end up here. And we can scale this by choosing x2 as we like. So that means we could also add half of it, for example, and that means we end up here. Or we could do twice that amount, we end up here. Or we could even go in the negatives, something like this. So as you can easily see, basically you have this point, and then you add any amount you want in this direction here, or in the negative direction. It's also fine. So you get this orange line in the end. Okay, so a solution space, in this case, looks like a line in two-dimensional space. All right, a third example. Same solution approach. Basically what I'm doing here is, again, I multiply this first equation by 2. I'm doing this because I see, well, here's a 3 and here's a 6. So if I multiply this by 2, I get 2 6s, and then I can subtract these and produce some zeros. And if I do this, turns out the whole left side is the same. And again, I get a 0 left-hand side after the subtraction process. This time, however, the right-hand side is not the same. So I get a non-zero right-hand side in that case. And that means here I get an equation, 0 equals -21. And of course, that can never be true, regardless of what x's I'm using. It's always false. And that means there is no solution to the system of linear equations, right? Those two equations cannot be satisfied at the same time. So the solution set, in other words, is the empty set. And what does the geometry of that look like? Well, again, each equation corresponds to a line in 2 dimensions here. And basically you have these 2 lines, and well, they just don't intersect anywhere. So there is no common point. That's why the solution space is empty. All right, any questions so far? For those following on the live stream, feel free to post your questions to TweetBack. The TweetBack link is on the Moodle page. I'll take a look at those later. All right, now let's get to the actual solution methods that we want to apply here. So to simplify things a little, we usually try to write down only the information contained in such a system of linear equations that is relevant to solving it. And what is not really relevant is repeating these variable names all the time. It doesn't really matter what those are called anyway, so we can just skip those, right? And this leads directly to what I'm calling tableau form here, or what will be called matrix form later. Basically what I do is I just skip all the pluses and I skip all the variable names. I write down only the coefficients, so the alphas here, and the right-hand side. Again, each row corresponds to one equation. Each column corresponds to one variable. Right? And it makes it hopefully easier to see the relevant information and to work with that without being distracted by unnecessary information. One more thing, if the system is homogeneous, so if this row is all zeros, then it's common to just leave it out. So if you write a system in that way without providing a right-hand side, that just means the right-hand side is 0. And so that you'll be able to distinguish those cases. The right-hand side is usually determined by a line like this. Yeah? Draw a line to split out the right-hand side. All right, and then particularly easy cases. Well, it's easy to solve a system in that form if it has what could be called a staircase form. Usually we refer to that as echelon form. Right? But the idea basically is to have something like a staircase with zeros below that stairs, and then we can just start solving it from below. So this last equation here, this only has one coefficient and zeros for all the others. So it's easy to solve this for the last variable, for the x3 variable. Once we have a value for x3, we can substitute that into the second equation, right? And then solve this for x2. And once we have values for x3 and x2, we substitute those. Okay, so that's the basic idea. We want to get our tableau into that form without changing the set of feasible solutions, of course, and then determine the solution set by doing this backwards. If we have 0 lines, then 0 lines are always at the bottom. Yeah, all 0 lines are always at the bottom. And for each row, all entries below leftmost non-zero element in the row are 0. So leftmost non-zero element in a row, let's take the second row for example, the leftmost non-zero element in there is this 1 here. And all entries below that 1 are 0. Right? So there's zeros below the staircase. That's what this says basically. And these leftmost non-zero elements, those are called pivot elements. If they exist, right? Of course, the 0 row doesn't have a pivot element. Okay, and then we just have to sort the rows so that the pivot elements from top to bottom move to the right. So basically each pivot element lies strictly to the right of all pivot. So for the next rows, all the pivots have to be strictly to the right of this one. So here's the next one. Here's the next one, also all pivot elements in row 3, and below we have to be strictly to the right of this one. Called echelon form. And the next one is just a technical remark. You'll sometimes see the wording reduced row echelon form. That's taking it a little further. If you want to reduce that form, you make sure that every pivot element is also 1, which was the case in our example, but you don't have to do a form. But also above the pivot. And if you do those two things in addition to what we've just seen, this would be reduced row echelon form. That is sometimes important in some applications, not so much in this course. All right. I don't think we need to take a look at that. Well, we've got the technicalities out of the way. Let's take a look at how Gaussian elimination actually works. So this is the solution method that we are going to employ. It's called Gaussian elimination. And the basic idea is to just use this addition and subtraction of equations to get a system that is in row echelon form, and then solve this using backward substitution. And the key observation here is that there are some operations that you can use and apply to the system of equations without changing the set of feasible solutions. Most simple possibilities, you can just exchange the order of any two equations. It doesn't really matter in which order you write them, yeah? So sort them as you want. What we also did is we multiplied an equation by a constant number. And of course you can do this without changing anything. If you think back to the geometry, an equation corresponds to a line. It doesn't really matter. So what matters for this line is basically the direction, right? It doesn't matter how long this direction is. It's just where it points. Right? So of course if you multiply an equation by 0, it vanishes. Right? You don't want that. You don't want to lose information, so make sure to not multiply something by 0. And that is especially important if you have a problem, for example, that contains a parameter. And you're doing these reformulations maybe based on values of a parameter. For example, if you multiply an equation by the parameter itself to make it easier in a way, you need to make sure the parameter is not 0. If it is, you would lose the equation. And you don't want that. So if that happens, you need to make a case distinction. And we'll see examples for systems with parameters in just a couple minutes. All right, and then the third, most complicated operation, you can add two equations together. I'm not saying subtract, I'm saying add, because I can just multiply one by -1 and then add to realize that subtraction. So you can just add one equation to the other and then replace one of those two equations by that sum. Not both, but just one, please. Right? Otherwise, again, you'd lose information. Okay, and by these operations, if you apply this in an organized way, you should be able to get every system of linear organized and easy to apply form that will hopefully prevent a lot of errors, especially as the systems become larger. All right, this is basically how this procedure works. You start with a system of linear equations, you transform it into tableau form, if it's not in that form already. You locate one of the leftmost pivot elements and make sure it's in the first row. So if necessary, exchange the order of equations. And then what you do is you use this first row here, and specifically the pivot element that's non-zero, and subtract suitable multiples of the first row from all the other rows, so that you get zeros below the pivot element. Right? That gives you your first staircase. And once this is done, you don't ever touch the first row again. You just operate on what is left here. Technically, you would touch the first column, this part of the first column, when doing the other operations, but there's all zeros anyway, so it doesn't matter what you do there. Right? So it will look like you also never touch those again. So you just repeat the process on this new reduced system until you get the complete staircase and possibly a few 0 rows below that staircase. And then you just use backward substitution to compute the solution. And if in the process you might find there are columns of that matrix that don't have a pivot element, so you can solve for that variable. And that will be the case if the system has more than one unique solution. If that is the case, you always get this kind of non-pivot columns. And the variables corresponding to those are called free variables. So what you can then do is choose any value you want for that free variable, and that will also always give you a value for all the other variables that you can solve for. And each possible choice of the free variables will give you another solution of your system of linear equations. So it's basically the same we have seen with this x2 thing over here, this here, right? So in that case, remember here's a pivot element. It's associated to x1. The second column, however, doesn't have a pivot. It would have to be here, but that's a 0. A 0 can never be a pivot element. Right? So here we have a free variable. x2 is a free variable, and any choice of x2 yields a feasible solution by just solving for x1. And then you get a set of solutions that is structured in this way. Possible for higher dimensional systems, you might not just have one free variable, but possibly several of those. Yeah, but it all works in the same way. All right, so you call these free variables. All the others that you can solve for are sometimes called bound variables. I usually not use that name, but free variables, that will appear often. All right. Finally, or maybe not. Maybe let's have a look at some examples before we do finally. All right, so you all tried your hand at the homework problem. Maybe let's take a quick look into Tableau form. So we just use the coefficients, and let me just mark those here. So here's a 1, here's a 0, right? This is simplicity 0x1. Here we have this 2. Here we have a 1 again, and here we have a 0 for the x2. And for the x3s, it's all 1s. Right? So our tableau looks like this. This first row is 1, 1, 0. The second row is 2, 0, 1. And the last row is 1, 1, 1. And then we also have the right-hand side here. This is just 1, 2, 3. And to distinguish the right-hand side from the coefficients, we just draw a line like this in our tableau. All right, and then we go about solving this. Specifically for the exam, when you solve a problem like this, please make sure to write small remarks somewhere on the board about what you are trying to do. For two reasons. First, it makes life much easier for correctors. And second, if you make a mistake in your computations, you can still show that you at least try to do the right thing. All right, so in this case, first we need to choose a pivot element in our first column if possible. So in this case, any non-zero will do. Here's a 0, so that can't be used, but either of these two is fine. We just use the first row so that we don't have to do any exchanges. Right, so this is going to be our pivot element. And that means we just copy the first row. Those will not be touched in any way. For the second row, we aim to get rid of that 1 here. We need to get rid of anything below the pivot, right? So for the second row, this 1 needs to go. We need to turn that into a 0. How can we do that? Well, we just subtract the first row from the second row once. 1 minus 1 will be 0, right? So this is what we do. And I'll just make a quick remark here on the side. I'll usually denote that like this, right? So from the second row, subtract row number 1 once. Well, what happens? We subtract this one from this one, so 1 minus 1 is 0. That's why we did that in the first place. Then we have 0 minus 2. That's minus 2. And then we have 1 minus 1, again 0. And finally, don't forget the right-hand side. 2 minus 1, that's 1. Okay, and for the third row, well, there's a 0 already, so we can just keep the third row as it is. Right? Third row is fine. So we just copy that. Okay, and that means currently we have one pivot here, and this is our current staircase. So our next step will be to look at row number 2, see if we can find a pivot in that row. And obviously we can. Here's a minus 2. Again, we could also use any other row below those that has a non-zero in this column here, so we could also use this row here. Yeah, that's fine. Let me use row number 2 for this demonstration. So what I want now is this here as my second pivot element, a minus 2. And now I need to get rid of all non-zero entries below that pivot. So there's just one non-zero entry here. There's one entry. How do I do that? Well, I just could add 1/2 of the second row to the third row. Right? That would mean I get 1 minus 1, that's 0. So that's what I do. I'll add 1/2 times row number 2 to the third one. So I just copy the first row once again. I also copy the second row now. I'm not touching that anymore. And now for the third row, well, it's 0 plus 1/2 times 0. That's obviously 0, so nothing changes here. Then here, 1 plus 1/2 times minus 2. That's 1 minus 1. That's 0. That's why I did this. And finally, we have 1 plus 1/2 times 0. Well, again, nothing happens, so the 1 stays. And finally, right-hand side, we have a 3 here and a 1 here. So 3 plus 1 times 1/2. That's 3 plus 1/2. 3 is 6 over 2 plus 1/2 is 7 over 2. So let's write it this way. 7 over 2 on the right-hand side. All right. Now we have this pivot here, this pivot here. There's our staircase. Well, this is the last row, so we can just complete the staircase. And this is the last pivot element. Right, so again, there's a pivot here, but nothing to do anymore because there's no more rows below that. Okay, so at this point, we have achieved echelon form. We could go on to achieve reduced echelon form if you wanted to, but it's not really necessary in this case. Yes? No, you don't need to write echelon form. I just write this comment here so that you know. You should usually compute echelon form, yes. simply because that avoids mistakes. I've seen too many easy mistakes made by solving systems like this. So I don't recommend you stop there. That depends. So for the exam, the answer depends on what is demanded in the problem statement. If I explicitly write, please compute echelon form, then I want to see the echelon form somewhere. If you skip that, you're losing points. If I'm just asking for the set of solutions, I'm fine with any other approach. As long as you're right and as long as you give suitable justification, which usually means showing your computations. Of course, you can also just take a wild guess and then prove that you're correct. It's also fine. All right, so this is echelon form. Final step, solve the system through backward substitution. So at this point, we need to remember what the names of the variables were and which columns they are associated to. So we have x1, x2, and x3, each associated to one of the columns. And we get the values by solving the corresponding equation for that pivot element here. So from row number 3, let me just write this like that here, we get the equation x3 equals 7/2. No need to solve anything anymore. Then from row 2, we get the equation minus 2x2 is 1. So that's easily solved as well. That means x2 is minus 1/2. Yeah, so there's a 0 here, so we don't need x3. And finally, from row 1, we get x1 plus 2x2 plus x3 is 1. We already know the values of x2 and x3, so we can just substitute those in here. That's x1 plus, let's see, x2 is minus 1/2. So we get 2 times minus 1/2 plus, and then x3 is 7/2. And then we solve that for x1. Well, that means x1, sorry, so this is minus 1. Minus 1 is minus 2/2 plus 7/2, so it's 5/2. So we get x1 plus 5/2 equals 1. And that means x1 is 1 minus 5/2. So 2/2 minus 5/2, that's minus 3/2. And finally, that means the solution set for our equation, that is x1 is minus 3/2, x2, let me also mark that in some color here, or maybe better like this. Then x2 was minus 1/2, and finally x3 was 7/2. Right, so just a single unique solution in this specific case. All right, any questions so far? That doesn't seem to be the case. Sorry? All right. Then let's maybe have a take at one more complicated example, and of course I'd like you to solve that one. So here it is. I'll give you, again, a system of linear equations, 3 equations, 3 variables, this time with a parameter. So all of this depends on a real parameter. I'm calling that one lambda. So for a parameter, lambda in the real numbers, solve the following system: x1 plus x2 plus lambda x3 equals 1. 1 plus lambda x1 plus 1 plus lambda x2 plus 2x3 equals 2. And finally, lambda x1 plus x2 plus x3 equals 1. All right? So this is the system I want you to solve. 2 things to pay attention to. If you multiply an equation by something that depends on this parameter lambda, make sure it's not 0. And the second, if you divide by something that depends on this parameter lambda, again, make sure it's not 0. If that happens, you need to make a case distinction at that point. Okay, so go ahead, give it a try. As usual, when you're done, please take a quick look at TweetBack and give me quick feedback on how hard you find the problem. Quick show of hands. Who of you is done already? All right. I was expecting that. A couple more minutes then. So for those that are done already, please compare your solution to your neighbor and see if you got the same results or find out why you didn't. So let's see how you're doing. Who's not done yet and not ready to give up? Okay, I'll give you one more minute. Please don't forget to submit your votes. right. Should be done by now, so let's take a quick look at your votes here. Not surprisingly, many of you found this pretty hard. I hope that's not so much because it is a problem where you don't know what to do, but it's just a problem that contains a lot of things at the same time, right? So it's a bit of a tedious computation, but hopefully it should be pretty clear how to approach that. So maybe let's have a quick look at how I try to do that, to unfreeze the projector. All right, so here's the system, and feel free to correct me at any point. I hope my computations are right. I try to just do that this moment. Right, so here's our original system. First, we can proceed normally. First thing we do is find a pivot element in the first row. That is possible because there is a 1 here, so we don't have to exchange any rows at this point. We could, we don't have to. I'm going to use this to produce zeros below that 1. To do that, we have to subtract 1 plus lambda times the first row from the second to get rid of that entry. And we have to subtract lambda times the first row from the third to get rid of that entry. And please note, this is not at all problematic. We don't need a case distinction at this point. Even if lambda is 0, what we're doing is we don't subtract anything, and that's totally fine, right? Not changing the system is fine. So no need to do any case distinction here. All right? That is hopefully the correct result of this reformulation. So now we have zeros here. And now the first problem appears. We're looking for a pivot element in the next row, the next column, column 2. We can't use this first line anymore, so it needs to be somewhere here. And unfortunately, there's a 0 here in this place, so this can't act as the pivot element. But there is possibly a non-zero here. So this might act as the pivot element if it's not 0. So at this point, at least make a quick note to say, well, the following computations are valid if this is not 0. Otherwise, I wouldn't have a pivot element. I'll take care of that case later. Right? So this is not 0, and that means lambda is not 1. So all the following computations are valid only if lambda is not 1. What we do is we exchange those 2 rows to get the pivot element in the place it needs to be, right here. And then we produce zeros below that pivot element. Well, that's easy because the zero is already there. Nothing to do anymore. Okay, and technically, by this point, we didn't even need that case distinction, right? We can exchange rows any way we want. That would only actually have played a role if we had to do some computations with that pivot element. We don't need to, so we could as well forget about that. All right, so this is how it looks now. So here's our staircase, right? And that means we have reached echelon form. And now we'll need to start with our backward substitution process. So first we need to solve this last equation here, right? This last equation that is 2 minus lambda squared times x3 equals 1 minus lambda. So to solve this, we just need to divide by that factor here. And now we actually need a case distinction. That factor could become 0. So we need to make a case distinction. If this is 0, then we'll see. If this is not 0, we can do the computations. So let's first find out when this is going to be 0, right? And to solve a problem like this, quadratic equation, you hopefully all know a couple of handy formulas, like this one here. So I just put in my coefficients, and I get the roots of this equation. And it turns out those are 1 and -2. Well, this 1 that has been suspicious before, that's nice. And also -2. So those are our extra cases at this point, right? That's when this expression here becomes 0. And to make things a little easier afterwards, this also helps us reformulate it. We can rewrite that expression in this way. Right? Once we know the roots, we can just write that as a product of these two linear factors here. And that makes it easier to divide by those factors later on. So let's get those extra cases out of the way first. Case lambda equals -2. Just substitute -2 in this expression here, and what we get is this matrix. And as you'll easily see, we have a 0 left-hand side here and a non-zero right-hand side. So there is an equation that says 0 equals 3, and that's just not possible. Okay, so in this case, there's no solution. Or in other words, I should write that explicitly, the solution set is the empty set. All right, first case out of the way. Second case, lambda equals 1. That's more interesting. Again, substitute the value into this tableau here. I just copied it, so it's easy to see what happens here. So in place of lambda, we write 1, and you'll see there's many zeros that appear here, right? In fact, the last two rows become 0, all of them. So that means we only left with one pivot element in that case. This is our only remaining pivot. And the variables that correspond to columns that don't have a pivot are free variables, right? Here we have x3 that corresponds to this column, x2 corresponds to this column, x1 corresponds to the column with pivot. So x2 and x3 are going to be free variables because there's no pivot in those columns. That means we can choose whatever value we want. We always get a solution. And the only thing we have to do is take this first equation and solve that for x1, right? And doing that, use this expression here. And we just write that in a structured way by saying, well, x1 is always constant. Here's one. Oh, I made a mistake here, by the way. Let me rewrite that in the correct way. So x1 is 1 minus x2 minus x3. That's how it should be. All right, so that is just this expression here. X2 is always x2. So we just get a 1 here and a 0 here. And x3 is just x3, so we get a 1 here and a 0 here. Right? And they don't have any constant parts, so 0's in here. And we get a possible solution for each choice of x2 and x3. So this is our solution set. And you can see this is not just one line anymore, like we had before, not just a single point. In this case, this is a plane in three-dimensional space, right? We have one point and then two possible directions, so this forms a plane. Okay, so those are the easy cases. Another remaining case, any possible value apart from those two extra values? Well, in this case, again, this is our row echelon form. Now we need to go about solving that, and we do that, well, x3, this is the equation for x3, so we just divide by this constant now, and we can do this. This is not 0, so we get this expression for x3, or if we simplify that a little, you can see this here can be cancelled out, so we get 1 over lambda plus 2. And then we take that, put it into this x2 equation here. Here it is, right, left-hand side. Here's the value that we just put in. And then solve this for x2. And doing this, hopefully again, yields x2, very same value, 1 over lambda plus 2. Right? And if you get something like this, that usually means that looks good. And finally, first equation. This is the first equation. I got that from here. Put in the values for x2 and for x3. Don't forget that lambda here. And again, simplify it, and what you get is 1 over lambda plus 2. So in other words, the solution in this case is one single point, and it looks like this. So each coordinate is the same, and I just took out that factor for it's more clearly to see what we mean here, right? Okay, so one single point for every value of lambda, apart from those extra cases -2 and 1, and we solved those already in the cases 1 and 2. Questions? Yes. Sorry? Questions, will we have to do all the cases in an exam? Yes, of course. If I'm asking for the set of solutions, then you'd have to go through all the cases. Hopefully there won't be too many. I guess that's one of the harder exam problems. I'm not quite sure where I got that from, actually. Any more questions about this one? Yes. Could you speak up a little? I'm having a really hard time understanding you. I guess the rest kind of wants to complete the session. Maybe you can just come up afterwards. All right, one more thing before we conclude. A little homework. I put that on a Moodle site with the slides. So you can take a look at that. We'll discuss that problem next time, but if you want, you can already take a quick look at that. So this is from an exam, 2016, determine all values for a parameter alpha, for which the following system does not have a solution, right? So in this case, you don't actually need to solve the system. I'm just interested in all the cases where it does not have a solution. That might make things a lot easier, or maybe not. Let me just write down the system. It's given by x1 plus 8 x2 equals 0. 2x1 plus alpha squared x2 equals 6. And 5x1 plus 5x3 equals 12. And pay attention, that is x3 right here, right? Not x2. So you have 3 variables in that equation system. Okay, if you want to take a look at that, and we'll discuss that problem tomorrow. So I'll see you tomorrow.